Hello and welcome everyone. Welcome to know about mathematics and its boundless world. Here I am going to present something and the topic is Introduction to Mathematical Science. So let us begin. First of all, let me introduce myself. Myself Utkarsh Raj, MSM first year IT Roorkee, enrollment number 2031-2039. This project is made under the noble guidance of Pratibha Ma'am, Associate Professor, Department of Mathematics, IT Roorkee. The motto is to make everyone familiar with the fields and scope of mathematical world. This will help you to understand the importance of mathematics and its many more application in physical world. So let us begin. So let me share you the content of this video, what I am going to discuss in this video. So whatever I am going to discuss in this video is compiled in this image, in which you can see that there are two broad categories, that is pure mathematics and applied mathematics. Basically, a math has two broad division, applied and pure. So we will learn about pure mathematics and its parts like algebra, analysis, combinatorics, geometry. Similarly, in algebra, we will go into the deep. So we will study about linear algebra, then abstract algebra, then number theory, then elementary. Similarly, analysis, we will go into the deep, combinatorics, and so on and so forth. Then after completing this pure mathematics part, we will move to the applied mathematics part, in which we will learn about probability, statistics, number theory, and numerical analysis, symbolic computation, and all these. After completing these two things, we will move to the research, like what are the research in mathematics, and then we will move to the modeling, like mathematical modeling. So let us begin. Mathematics. I am not going to define mathematics in a very big words. So in simple word, I am telling you, the mathematics is the science and study of quality, structure, space, and change. Adding to that, through abstractions and logical reasoning, mathematics evolved from counting, calculations, measurement, and the systematic study of shapes and motion of physical object. So this is basically what the mathematics is. So everybody, or you can say you are also familiar with the mathematics, what is mathematics and all. So let me tell you that mathematics has two broader divisions, applied mathematics and pure mathematics. So first of all, let us introduce pure mathematics. So what is pure mathematics? As you know, mathematics is both an art and a science, and the pure mathematics lies at its heart. So what is the pure mathematics? Pure mathematics explores the boundary of mathematics and pure reason. So it has been described as that part of mathematical activity that is done without explicit or immediate consideration of direct application. So you may think, if there is no direct application, then why we are studying this pure mathematics? Why are we not focusing on directly applied mathematics? So the thing is, the applied mathematics has its fundamental thing from pure mathematics. Like you can see the last statement, although what is pure in one era often become the applied later. So what is the part in applied mathematics? That was a pure mathematics part. It was originated from a pure mathematics. So if you are studying something, if you are studying applied mathematics also, so there is a use of pure mathematics. So let us see what we are going to study about pure mathematics. In pure mathematics, we have first of all algebra, then analysis, then combinatorics, and then after we will learn about geometry. So let's begin the chapter of algebra. Algebra has a Arabic or origin, and it means reunion of broken part, or you can say bone setting. Algebra is one of the broad part of mathematics, together with number theory, geometry, and analysis. In its most general form, algebra is the study of mathematical symbol and the rules for manipulating these symbols. It is a unifying thread of almost all the mathematics. It includes everything from elementary equation solving to the study of abstractions such as groups, rings, and field. We will see the what is all those things in the further slide. So let's move on. So the first part is linear algebra. Linear algebra is central to almost all areas of mathematics. So it is considered as the center part of mathematics. It has so many uses. For instance, linear algebra is a fundamental in modern presentations of geometry, including for defining basic objects such as lines, planes, and rotation. Also, functional analysis, branch of mathematical analysis that we will learn in a further slides, may be viewed as basically the application of linear algebra two spaces of functions. Linear algebra is also used in most sciences and field of engineering because it allows modeling many natural phenomena and computing efficiency with such models. So here you can see the use of linear algebra in different part of the physical world. In engineering field we are using, in computing field we are using, in mathematical modeling we are using it, or you can say in geometrical part we have the use of linear algebra. Then we have elementary algebra. Elementary algebra encompasses some of the basic concept of algebra, one of the main branch of mathematics it is considered. So like it's begin in the secondary school, and when you are in secondary school you have the elementary algebra part. So before that you were learning about arithmetic. Arithmetic deals with specified number. It means it deals with a number which has a fixed value. But what the algebra has done, algebra has its unique property. Its unique property is that algebra introduces quantities without fixed value, that is known as variable, and it has its own use. This use of variables entails use of algebraic notation and an understanding of the general rules of the operators introduces in arithmetic. So what we are operating in arithmetic and combining those two things, like arithmetic plus algebra, it means like constant plus variable. When we are combining these two and operating something, we have a wide variety of use. So the use of variable to denote quantities allows general relationship between quantities to be formally and concisely expressed, and thus enables solving a broader scope of problem. You may be familiar with the physical problems, like in physics also you have seen that like to establish some relationship between some of the quantities we are considering a variable. So variable has its own use, and variable is given by or introduced by that algebra. Now we have another part of algebra, that is abstract algebra. In this part, this is a broad division of mathematics you can say, and it is called as modern algebra. So the basic thing is, in this we are studying the algebraic structures. What is algebraic structure? Algebraic structure includes groups, fields, rings, modules, vector spaces, lattices, and algebras. So all those things, like lattices, you have learnt about lattices in the solid state part in chemistry also. So all those things is called algebraic structure. So the term abstract algebra was coined in early 20th century to distinguish this area of study from other part of algebra. So this is from historic point of view. And then what is the use of this? So there is an algebra called as universal algebra, and universal algebra is a related subject that studies type of algebraic structures as a single object. For example, the structure of groups is a single object in universal algebra, which is called variety of groups. For example, just take the example of that figure. It has so many small cubes, but combining all these cubes into a group, we have a big cube. So these things is called like structures of groups, like small groups, combining them and forming it is or considering it is as a single group. So all these studies or structure of algebras comes under this abstract algebra part. Then we have number theory. Number theory, or you can say arithmetic or higher arithmetic, it is in older use also, is a branch of pure mathematics devoted primarily to the study of the integers and integer valued functions. So this number theory is particularly in use in to study about integers and integer valued function. And German mathematicians Carl Friedrich Gauss said that mathematics is a queen of science and the number theory is a queen of mathematics. So this statement, you can imagine how important this number theory is. So the older term for the number theory is arithmetic. By the earlier 20th century, it has been suppressed by a number theory. So the thing is, like, number theory has its own importance, because without having number theory we cannot assume a mathematics. So that is why it is called as the queen of mathematics, and it has very big use, like in determining the prime numbers property, in determining the whole numbers property, in determining some of the series. So all those things comes under this number theory part. Now begin the chapter of so likewise from this number theory we have ended the chapter of algebra. Now we are moving to the chapter of mathematical analysis, the second part of pure mathematics. It is a branch of mathematics dealing with limits, differentiation, integration, measure, infinite series, and analytic function. So the word analysis emphasizes something. What it emphasizes? It said that the how we are analyzing something, how we are analyzing some graph, how we are analyzing some functions. So all these studies comes under this mathematical analysis part. So these theory are usually studied in the context of real and complex number and functions. Analysis concept evolved from calculus, which involves elementary concept and techniques of analysis. Analysis may be distinguished from geometry, however, it can be applied to any space of mathematical object that has definition of nearness, specified distance between objects. So all those things, like in calculus we are studying about differentiation, limits. Limits is what? When the nearness is specified. The study of that nearness is the analysis part, comes under this analysis part. So in this we will learn about calculus analysis, function analysis, harmonic analysis, and then complex analysis. So let's begin the calculus analysis. Multivariable and vector calculus. So multivariable calculus is also known as multivariate calculus. This is calculus analysis part. Is the extension of calculus in one variable to calculus with function of several variables. So multivariable, the word multivariable only denotes that when you were using the part calculus with one variable, now just extend this to the function with several variables. The differentiation and integration of functions involving several variables rather than just one. So this comes under this multivariable and vector calculus. So the vector calculus plays an important role in differential geometry, the use of vector calculus, and in the study of partial differential equation. It is used extensively in physics and engineering, especially in the description of electromagnetic field, gravitational field, and fluid flow. So here you can see the use of vector calculus, the use of multivariable calculus. All those things comes under the physical use, like in physics and in engineering we are using all those things. So the first vector calculus was developed from a Quaternion analysis by J. Willard Gibbs and Oliver Heavenside near the end of 19th century, and the most of the notation and terminology was established by Gibbs and Edwin Bidwell Wilson in their book 1901 book Vector Analysis. So these were the guy who invented or who compiled everything vector analysis part in a book. So in the right side we have Edwin Bidwell Wilson, and the left side we have Gibbs. So let's move on. Then we have function analysis part. In function analysis, it's a branch of mathematical analysis, the core of which is formed from study of vector spaces endowed with some kind of limit related structure, and the linear functions defined on these space and respecting these structures in suitable sense. So the functional analysis, the part which we are analyzing some function. We have given us some functions, and how we are analyzing what is the maxima of this function, what is the shape of this function, how it is going to tend to infinity, what is the limiting value of those functions. All those things comes under this function analysis part. The term was first used in Hedmard's 1910 book on the subject. However, the general concept of functional had previously been introduced in 1887 by the Italian mathematician and physicist Vito Volterra. So this is from a historic point of view when this function analysis part was introduced firstly. In modern theory, introductory text of functional analysis, the subject is seen as the study of vector spaces endowed with topology, in particular infinite dimensional spaces. So all those things like the vector spaces are also related with this function analysis in the modern ways. So let's move on. We have then harmonic analysis. Harmonic analysis is a branch of mathematics concerned with the representation of function or signal as a superposition of basic waves, and the study of and the generalization of the notion of Fourier series and Fourier theorems. In the past 2 centuries, it had become a vast subject with application in areas of diverse as number theory, representation theory, signal processing, quantum mechanics, tidal analysis, and neuroscience. So here the harmonic analysis part of mathematics, or you can say branch of mathematics, which deals with the wave, which deals with the superposition of wave. So the wave, you have a use of wave in day-to-day life. You are telling something, the sound is propagating through a wave. Light has some nature of electromagnetic wave. Similarly, you are using mobile phone, that signal is sending through a wave. So all those things, analysis of this wave and its superposition, how it is traveling from one part to other, and how we are just generalizing those things, that all those things comes under this harmonic analysis part. Okay, now moving on to the complex analysis part. We have the complex analysis, traditionally known as theory of functions of a complex variable. It's a branch of mathematical analysis that investigate functions of complex number. So this is particularly for a complex number function. When we are dealing with a complex number function, then this function complex analysis part, it comes into the act. It is useful in many branches of mathematics, including algebraic geometry, number theory, analytic combinatorics, applied mathematics, as well as in physics, including the branch of hydrodynamics and thermodynamics, and particularly quantum mechanics. So here you can see how pure mathematics has its use in applied mathematics or in a physical world. So by this we are ending the analysis part. So mathematical analysis has its component, and we discussed about all those things. Now moving on to the geometrical part, we have geometry, a branch of mathematics, pure mathematics. It is a branch of mathematics that studies the size, shapes, position, angles, and dimension of things. So the flat surface shapes like squares, circles, and triangles are the part of flat geometry and called as 2D. Similarly, we have a three-dimensional object. So not only have fixed or regular shape, we have so many irregular shapes. So studying about these shapes, these physical shapes that we can see, so all these shapes comes under the geometric part, and in that part we will learn about discrete geometry, then manifolds, then differential geometry also. So moving on to the discrete geometry part. Discrete geometry, it is a branch of mathematics that study combinatorial property and constructive method of discrete geometric object. And the discrete geometry involves finite or discrete sets of basic geometrical object. So it has some set kind of thing. It has some finite set, it has some infinite set. So finite or discrete set we have in this geometrical part, in discrete geometry. So it such as the shapes we are learning in this is points, small point, lines, planes, circles, spheres, polygon, and so on and so forth. So these are some of the objects that we are studying under the discrete geometry part. The subject focuses on the combinatorial property of these objects, such as how they intersect one another and how they may be arranged to cover a large object. So how we are drawing something, like when we are connecting to some points to another point, we got a line. Similarly, how we are combining those things and constructing a larger object. So all these studies comes under this discrete geometric part. So moving on to this, now we have manifolds. In mathematics, a manifold is a topological space that locally resembles Euclidean shapes near each point. More precisely, an n-dimensional manifold is a topological space with the property that each point of the neighborhood that is homomorphic to the Euclidean space of dimension n. So we have like n-dimensional. Till now you have you may be familiar with the one-dimensional, two-dimensional, and three-dimensional. So here we are talking about n-dimensional object. So one-dimensional manifolds include lines and circles, simple, that you can be clarified with this. Two-dimensional manifolds also include some surfaces, for example the plane, the sphere, and the torus, which can be embedded in three-dimensional real space. But also the clean bottle and the real projective planes, which will always self-intersect when immersed in three-dimensional real space. So these are some of the things, like how we are defining some object in 1D, how we are defining in 2D, how we are defining the 3D, how they are intersecting to each other. So this study of this type kind of shape comes under this manifolds part. So moving on to that, we have differential geometric part. Differential geometry is a mathematical discipline that use the technique of differential calculus, integral calculus, linear algebra, multilinear algebra to study the problem of geometry. Here you can see the link between algebra and geometry, the link between mathematical analysis and geometry. In the algebra, we in differential geometry also includes algebra. Differential geometry also includes differential calculus and integral calculus, which is a part of mathematical analysis. So here you can see like how they are interlinked. The theory of plane and space curves and surfaces in three-dimensional Euclidean space formed the basic for development of differential geometry. During the 18th or 19th century, it is developed. So why it is developed? The reason is crystal clear. So the differential geometry is closely related to the differential topology and the geometric aspect of the theory of differential equations. The differential geometry of a surface captures many of these keys, ideas and techniques endemic to this field. So we have so many things like the use of differential geometry has like differential equation we are using for something something to relate with the differential geometry. So these are the things in differential geometric part. So with this we are ending the geometry part and moving to the combinatorics part. That is the third part of pure mathematics. Combinatorics is an area of mathematics primarily concerned with counting both as means and ending in obtaining result and certain property to finite structure. It is closely related to many other areas of mathematics and has many applications ranging from logic to statistical physics, from evolutionary biology to computer science. So you can think in biology also we have the use of this combinatorics part. So here you can see how mathematics is with the different part of science. The full scope of combinatorics is not universally agreed upon. According to H.J. Reiser, a definition of the subject is difficult because it crosses so many mathematical subdivisions. So it is very difficult to define, or you can say it is very difficult to define that combinatorics part. So whatever we will in combinatorics, we will learn about graph theory, extremal combinatorics, enumerative combinatorics. So let's begin with the graph theory. So in mathematics, graph theory is a study of graphs, which are mathematical structure used as model pairwise relation between objects. A graph in this context is made up of vertices which are connected by edges. So this is a graph. You mainly draw a graph. So in these are the like connectivity between some points, some vertices with the help of the edges. So this is like a study of model, study of some shape. A distinction is made between undirected graph. There is two types of graph, undirected and a directed. Undirected graphs where edges linked two vertices symmetrically, okay, and the directed graph where edges link two vertices asymmetrically. So these are some of the definition of undirected graph and the directed graph. Graphs are one of the prime object of study in discrete mathematics. So it is also in discrete mathematics also we have learned that the graph is also very much important. So after this we have like extremal of combinatorics. Extremal combinatorics is a field of combinatorics which itself a part of mathematics. Extremal combinatorics studies how large or how small a collection of finite objects is. If it has to satisfy certain restrictions. If we have given some restriction, then how large that object is and how small that object is. All these studies comes under this extremal combinatorics. Much of the extremal combinatorics concern classes of sets. This is called extremal set theory. So in set also we have some components. Maybe when we are comparing one set to another set of having same component, of having same kind of component, then we can define like, yes, this set is a large set or this set is a small set. So these comparison and all those things comes under this extremal combinatorics. Suppose we are given a finite set of non-zero integers and are asked to mark as large a subset as possible of this set under the restriction that sum of any two marked integer cannot be marked. It appears that independent of what the given integer actually are, we can always mark at least 1/3 of them. So these are some of the situation. These all those things comes under some restriction. You have given some restriction, you have given some sets, then find out this, find out the subset, find out the universal set. So all these studies comes under this extremal properties, extremal combinatorics property. So moving on to this, we have enumerative combinatorics. Enumerative combinatorics is an area of combinatorics that deals with the number of ways that certain pattern can be formed. Two examples of this type of problems are counting combinations and counting permutation and combinations. These are like part of this enumerative combinatorics. Although counting the number of elements in a set is a rather broad mathematical problem, many of the problems that arises in application have a relatively simple combinatorics descriptions. So all those things are like permutation and combination. You can see permutation, how we can count something having different kind of patterns. The simplest such functions are closed formulas, which can be expressed as a composition of elementary functions such as factorials, powers, and so on. So all these combinatorics, permutations and combinations kind of thing came under this enumerative combinatorics. Combinatorics basically the study of counting for a given certain condition. So likewise, we have ended the session of combinatorics. So we have learned about algebra, we have learned about analysis part, we have learned about geometry part, and we have covered the combinatorics part. So likewise, we are ending the pure mathematics part and now moving to the applied mathematics part. Applied mathematics, so let us define it. Not only define, I just want to give you a brief words how can we say like what is applied mathematics. Education gives you not only the knowledge but also the ability to organize and use that knowledge profitably. So applied mathematics is geared toward providing the student with the ability to use a variety of mathematical and computational tools to solve problems in various fields. It is a combination of mathematical science and specialized geometry, specialized knowledge. So applied mathematics is a kind of thing, the application of the mathematics in the real world. Okay, so in applied mathematics we will learn about probability, we will learn about statistics, we will learn about numerical analysis, we'll learn about symbolic computation. So let's begin the chapter of pure applied mathematics with probability. Probability, all you know, probability is a branch of mathematics concerning numerical description of how likely an event is to occur, or how likely it is that a proposition is true. The probability of an event is a number between 0 and 1, whereas roughly speaking 0 indicates impossibility and the 1 indicates certainty. Something is very much sure, that's probability is 1. Something is not at all possible, the probability is 0. The higher the probability of the event, the more likely it is that the event will occur. It is used wisely in areas of study such as statistics, mathematics, science, finance, gambling, artificial intelligence, machine learning, computer science, game theory, and philosophy to, for example, draw inference about an unexpected frequency of event. Probability theory is also used to describe the underlying mechanics and regulatory of complex system. So here you can see like how it is related. So there are so many use of probability, the application of probability in direct life. Directly you are using the probability in the in your physical life. Before this applied mathematics, in pure mathematics we have learned something, but the direct application is not very much clear. Here you can see the direct application of something, some mathematical tools in our day-to-day life. So this is the probability, and in the picture you can see the impossible thing, unlikely, even chances, likely, certain. So all those things comes under the probability. Moving on to the statistics. Statistics is a discipline that concerns the collection, organization, analysis, interpretation, and presentation of data. So if we have some data, how we are analyzing them, how we are collecting them, how we are organizing them. So all those things comes under the statistics. In applying statistics to scientific, industrial, or social problem, it is conventional to begin with a statistic population or a statistic model to be studied. So first of all, we must learn about statistic model, how we are going to use that data into certain model. So statistics deal with every aspect of data, including the planning of data, collection in terms of design, survey, and experiment, all those things. In day-to-day life, we have a huge role of statistics. When census data cannot be collected, statisticians collect data by developing specific experiment designs and survey samples. So with some samples, we are using that sample to come into some conclusion. So the studying of statistics is very much important in our day-to-day life, in our physical world. An experiment study involves taking measurement of the system under study, manipulating the system, and then taking additional measurement using the same procedure to determine if the manipulation has modified the values of a measurement. So all those things, like how we are manipulating something, how we are additionally measuring something, so how we are representing all the big data in the simplest manner in a pictorial view. Here you can see how a bar graph, how a pie chart, how a graph, how a comparison between two graphs is represented to make the study easier, to make everyone understandable. So all those things comes under the statistic. It has a direct application in our day-to-day life. Here you can see how interesting this applied mathematics part is. So all those things comes with the help of pure mathematics only. We have that experimental part, we have that manipulating, calculation, all those things were related with the pure mathematics to this applied mathematics. Now moving to the numerical analysis part. Numerical analysis is a study of algorithm that use numerical approximation for a problem of mathematical analysis. Numerical analysis naturally finds application in the field of engineering and physical science. But in the 21st century, also a life science, social science, medicines, business, and even the arts have adopted elements of scientific computation. So the growth of computing power has revolutionized the use of realistic mathematical models in science and engineering. The subtle numerical analysis is required to implement these detailed model of the world. For example, ordinary differential equation appears in celestial mechanics. Numerical linear algebra is important for data analysis. Stochastic differential equation and Markovnikov chain are essential in stimulating living cells for medicines and biology. So here you can see how this numerical analysis has its role in the physical world. Actually, this analysis part, mathematical analysis part, we have learned in the pure mathematics, and those application came into the role in the physical world later. So earlier this numerical analysis was a part of a pure mathematics, then later it has become the part of a applied mathematics. Since the mid 20th century, computer calculate the required functions instead, but many of the same formulas nevertheless continue to be used as a part of software algorithm. So in software also, in computer science also, we have this use of numerical analysis. So here you can see how important these things are. Now we have symbolic computation, the fourth part of algebraic applied mathematics. In mathematics and computer science, computer algebra, also called symbolic computations or algebraic computations, is a scientific area that refers to the study and development of algorithm and software for manipulating mathematical expressions and other mathematical objects. Although computer algebra cannot be considered a subfield of scientific computing, They are generally considered a distinct field because scientific computing is usually based on numerical computation with approximation floating point numbers, while symbolic computation emphasizes exact computation with expressions containing variables that has no given value and are manipulated as symbols. So all those things like symbolic computation included that computer algebra, how mathematics and computer science are related to each other. So the software application that perform symbolic calculations are called computer algebra system, and with the term system alluding to the complexity of the main application that include a method to represent mathematical data in a computer, a user programming language, a dedicated memory manager, a user interface for input output of mathematical expression, a large set of routine to perform usual operations like simplification of some expression, differentiation using chain rules, polynomial. All those things comes into the role, like how you are using a calculator in which you are giving an input and you are getting some output with performing some certain operation. So all those things, all the programming of those system comes under the symbolic computation part. So likewise, this has a very huge role in our day-to-day life because software industry is increasing much faster than earlier. So symbolic computation has a great role in the physical world. So moving to that, we have ended the applied mathematics part also, although it is a very small part, but yes, it is very important. Then we have research. What is research? Research is the act of trying to find the answer of interesting question. So what is the research? Research is trying to find the answer to a certain interesting question. So first of all, giving this in how we can relate it with the mathematics. Is there any tricky question? Is there interesting question in mathematics that we are trying to find the answer? So we would define math research to be the act of trying to find the answer of interesting math question. So here are two types of mathematical research commonly referred as theorem problem solving and the theory building, where there are two various kind of research. Typical characteristics of theorem problem solving type research is to try and tackle a famous open problem, usually stated in the form of conjecture as a valid statement or specification of a problem. So quite often this will entail spending a lot of time learning the relevant material, analyzing particular attempt at a solution, trying to figure out what they don't work, why they don't work, if we are attempting in some way using some path, and if it fails then why that don't work, and hopefully come with some improvement of the existing attempt or a whole new attempt that is good change for the working. So we have to attempt so many times, we have to make an attempt that some way, and if it fails then back and start a new attempt, or just manipulate those previous attempt to have a good attempt, have a good change of working. Similarly, theory building is somewhat different activity that involves a new structure or extension of existing structure. Usually the motivation behind the study of these new structure is coming from a desire to generalize, or there might be a need to these structure to exist due to some application in mind. Typical activity would include a lot of reading on relevant structures, understanding their global role, figuring out what generalization or new structure would make sense, what the aim of the new theory will be, and then a long process of proving basic structure theorem for a new structure that will necessitate tweaking the axioms. So research, first of all, what could be the problem, what is the interesting question that we are going to answer. So first thing in the research is to get that question. How do we get that question in our mind? It is not available in Google, it is not available in some books. You have to create some situation, you have to create a think about some interesting question, then try to solve it through using some of the mathematical tools. If you fail in one attempt, then try other attempt or modify that same attempt. So the research is the only thing is like finding a question using some mathematical tools, finding that answer with various attempts. Maybe you got answer in a first attempt also, maybe you may got the answer in after 100 attempt also. So this is the kind of the research is. So the aim of the research is to that there must be a new theory, okay, that is going to impact on the previous one. Okay, so the impact is must, like if we are proving something that has no impact in the real world, then it has no use of research. So research must be that which impact the day-to-day life, or which impact the previous things. So here the research is kind of thing. Then moving to the modeling, like after finishing the result, we have mathematical modeling. So what is mathematical modeling? Mathematical modeling is the art of translating problems from an application areas into tractable mathematical formulation, whose theoretical and numerical analysis provide insight, answers, and guidance useful for originating applications. So what is mathematical modeling? Mathematical modeling is indispensable in many applications, is successful in many further applications, gives precision and direction for a problem solution. Well, a thorough understanding of a system modeled prepare the way for better design or control of a system, allows the efficient use of modern computing capability. So what is actually a mathematical modeling is? Mathematical modeling is like solving some of the natural phenomenon using a mathematical techniques. Like we have some mathematical model. It first of all it will have a problem statement. Then we will move to the theory, what theory we are going to use. Then using the numerical method and some programs, we going to the report. So the every part of mathematical modeling is connected to each other. So what is the thing is that we have some of the problem, natural problem, that we are going to model through using a mathematics, in which we are some of the times we have like for example we are modeling air pollution problem, in which how the lungs get affected. So first we will consider the size of a air particle which will affect the lungs, how it is going to the trachea, how it is affecting, how much surface area of the lungs is, how big the how many particle can affect the lungs. So the deep study of this, the whole thing, the whole problem, using mathematics and using many things, not only mathematics, using computer programming also, using so many subjects, combining all those things, using biological activities also. So all those things like these called a model, mathematical model. So likewise the modeling is also a very big example of applied mathematics. Like we are applying mathematics to the real world. We are solving certain problem, we are solving certain natural problem with the help of mathematics. So likewise mathematical modeling has also its own use. So with this I would like to end my video. Like we have been through so many things. We have got to know about pure mathematics, then applied mathematics, then we have a short glimpse on research, modeling, and now coming to the end of this video, I will end this video with a quote by Albert Einstein: logic will take you from A to B, but imagination will take you from everywhere. So the thing is, like how you engage your brain, the more you imagine something, the more sharpen your brain will be. Mathematics is that subject which provides you a platform to imagine something, which provide you the platform to engage your brain, and that is why mathematics is called queen of science. The mathematics has, it's not only, if you are not interested in mathematics, no problem, but you must learn a basic mathematics, because it not only provide you a grade, it not only provide you a marks in an exam, it sharpen your brain, it sharpen your logical thinking capability. So mathematics has its wide use. It has a boundless world, boundless boundaries. So you can learn so many things in mathematics. You can learn, if you have interest in pure mathematics, do research in pure mathematics and try to convert it into the applied one, a big task. If you have some certain question problem statement, then try to analyze that statement through a mathematical way. So thank you for listening. Thank you for being the part of this video. Thank you.